Hello everyone, good morning. Okay, so welcome. Okay, so we are basically nearing the end of the semester. Okay, so in terms of lecture slides, we have two main slides plus another, just a few more material to cover. Okay, so today basically we will finish up the chapter. We'll finish the chapter on comms. All right, we will talk about thread flags, event flags, and message queues. Okay, and then we will look at a short demo on how it works. Okay, and that is something you will also do in the lab manual. And then I will also move on to the next set of slides on memory. All right, and next week will be, I think, a shorter lesson. Probably within 1 hour, we should be able to finish up the rest of the slides and at the same time have some discussion on the exam. Okay, so just today and one more week. All right, so let's get started. Okay, so on Friday, actually, I came by. Those of you who saw me, I came by to the lab just to walk around and have a look in the morning part. Okay, so seems to me that everybody is doing very well. Okay, and it's clear on putting things together and getting it to work. All right, so if you have any major issues that you are stuck with, of course, the TAs are there, but if the TAs are also not very sure, then you can, of course, consult me as well. Okay. And of course, another thing that I also notice is when you are trying out things, all right, with the RTOS, uh, in the labs and all, we of course cover all the important concepts. But if you are keen on trying something that is different or that's not covered in the class, you're of course free to do so. Okay, so by the end of this set of slides, okay, you would already have all the sort of tools that you need to put your entire architecture together. Okay, and that is definitely more than enough. Okay, to uh, implement the requirements for the project. Okay, um, so you are free to choose what you want to do. Okay, in terms of the implementation, as long as you have that minimum number of tasks and those requirements are fulfilled. Okay, but how you want to pass data around, how you want to synchronize is up to you to decide. Okay, but of course there are some things that are already specified in the document which you need to follow. Okay, but other than that, the architecture wise, you are free to decide. Okay, so let's finish up this chapter first, all right, and then we'll talk a bit more on that in a while. Okay, so in this chapter, basically, we are going to be looking at messaging and synchronizing. Okay, so in the last lecture on the semaphores, we actually did have a look at how we can synchronize using semaphores. All right, so we saw the idea that, so if I have two tasks, T1 and T2, okay, one task that is running can call sampan. Okay, that means to take the semaphore. Okay, and if let's say the semaphore is not available, all right, that means the current semaphore count is 0. Okay, then you will go to a block state. Okay, and when another task that is uh, then able to run and maybe post a semaphore, okay, then whichever task that was waiting for the semaphore can become unblocked, so can go to a ready state. All right, so that is one way of synchronizing between tasks or between interrupt and task. Okay, so now we're going to look at another two different ideas. Okay, so we have looked at semaphores. We have also looked at mutex, but mutex is more for the protection of critical regions, okay, which have shared data across different tasks. Okay, and then now we're going to be looking at flags, events, and mailbox, or what we call message queues. Okay, so let's look at the first one, which is flags. So these thread flags, they are already automatically pre-built within the thread. So you do not need to explicitly create thread flags. Okay, when you create a new thread, it already comes with flags. Okay, and each thread has 31 flags from 0 to 30, and another thread can set the thread flags in some other thread. All right, that means T1, okay, can set the flag, okay, of T2 or T3 or any other task. Okay, in order for me to do that, I must know the thread ID. Okay, so the thread ID is not the thread name. Okay, when we create a thread, okay, when we call OS thread new, we pass in the name here. This is the thread name. Right? This is basically the task or the code that is referenced by this name that will run, okay, for this task. But when I call OS thread new, the OS will also automatically assign me a unique ID, okay, to keep track of the task and the state and so on. So that is, of course, all of this is stored within the task control block. Okay, so within the task control block, you have all this information. And when I want to reference a thread in any of the OS kernel functions, I need to use the thread ID, the TID. Okay, so this thread ID is the return value that I get when I create the function. So in the past, we did not actually capture this return ID. Okay, but now we will need to do it. Okay, because we need to use this ID. Okay, to allow a task to set the flags of or to allow other tasks to set this current task flags. Okay, so this thread ID is something that you need to now capture back. So before that, I also need to create a thread ID variable. Okay, so I need to use OS thread IDT to create the thread ID variables that will capture this return value when I call OS thread new. Okay, so once I capture this thread ID, I can now set the flags of that particular thread, and at the same time, a thread can also wait for specific flags to be set, okay, within its execution. All right, so basically what we are doing is one task can set the flags of another task, and whichever task is waiting for some flags to be set can be put into a block state, all right, until it is able to run. Okay, so let's look at an example here. Okay, so in this example, okay, we have two tasks, LED on and LED on and LED off. So LED on, what does it do? It calls the LED on function. So in this case, it switches on the LED. Okay, switches on the LED. That means technically you can say that I set the output to a 1. All right, so this is a 0, this is a 1. So I set the output to a 1. Once I do that, I call OS thread flag set. Okay, so now when I call thread flag set, I need to specify which task I'm talking about and which flag I'm setting. Okay, so in this case, I am going to set the flag for the task which is tied to TID LED off. Okay, so TID LED off is now tied to this. Okay, so that code is not shown here, but basically when I call OS thread new, okay, when I call OS thread new, okay, and I call this and I associate this with LED off function, okay, it will return me the ID. So that ID is basically captured earlier on over here. Okay, so this is what we need to sort of execute in the main code. Okay, that means after OS kernel initialize, when I call OS thread new, now I need to make sure I do this. I capture the ID. Okay, now so this TID LED off is now the thread ID of this task that I've created, which is LED off. Okay, so now in LED on, I can now reference this task with this ID, and now I say that I want to set this particular flag to 1. Okay, so within the TID LED off task, there is already a pre-built flags 0 to 30. Okay, and now I'm going to set for bit 0. So I'm going to set bit 0, okay, to a value of 1. Okay, so that is what I'm doing here. And once I do that, I call OS delay. That means I go to a block state. So after this, I will block for 2 seconds. So LED on is blocked, okay, for 2 seconds, and then I will come back. Okay, so once LED on goes to the block state, what happens? Then LED off can start. All right, and when LED off starts, okay, uh, the first thing that it does is it calls OS thread flags wait. Okay, so when I call OS thread flag wait, I do not specify any task ID because it is referencing its own task. Okay, only when I do thread flag set, I specify the task ID depending on which task I want to set for. When I do thread flags wait, it is referencing its own task. So what I'm saying is I want to wait for bit 0 flag to be set. Okay, and then I say two options, wait any and wait forever. So wait forever, we know that means if this event does not happen, I will go to a block state. Wait any, what is wait any? So over here you can see that I have some options. Okay, wait any and wait all and no clear. So later we'll look at another example, but basically wait any means if I'm waiting for a few flags to be set, I can choose to carry on as long as any one of the flags are set. All right, but in this case, okay, I'm just going to use wait any. The next example we'll see the wait all. All right, so since this flag was already set by LED on, the LED on already set this. So when I call thread flags wait the very first time, it is already, the flag has already been set. So I do not need to wait or do not need to go to any block state. Okay, so I straight away call OS delay for 500. Okay, so what happened is once this task starts to run, LED off, it starts to run, you will then go to a wait for 500 millisecond. So once the delay is complete, when it comes out, it will call LED off. That means I bring the logic back to 0. Okay, but the moment I finish LED off, what happens? I go back and wait for the next time. Correct. So in this case, once the flag has been read, it will clear to 0. So the next time, the moment I look back and I wait for the flag, I see that it is 0. So since the flag is 0, I will now wait until somebody set the flag. Okay, so this task LED off will now wait indefinitely until somebody set the flag. Then what is happening? LED on is still in the block state, but once the 2 second is up, it will come back, it will set the on again, all right, and then it will set the ID LED off task, the flag to 1. Correct. So it will, once it's set to 1, then this task will be able to unblock, all right, and go to a ready state. And once this task go to a delay, then this task can carry on. All right, so you can see that we are now performing this LED on and off, but now two different tasks are controlling it. One task is switching on, the other task is switching off. Okay, and the duration of the on time and this periodic interval is managed with the way we use the OS delay. Okay, so this is one way in which you can synchronize the behavior of different tasks, okay, using LED thread flags. Okay, so thread flags is one way and is a built-in utility of the thread the moment you create a new thread. Okay, so this is something you can try. Now in this example, we have 3 threads. Okay, and in these 3 threads, we have thread 1, thread 2, thread 3. Now let's assume, okay, T1, T2, T3. Now let's assume that T1, T3 runs first. Okay, so when T3 runs first, okay, the first thing that it does is it calls OS thread flags wait. Okay, and you can see that now it specifies 3. That means in terms of the flags, both flag bit 0 and bit 1 both must be 1. And I say OS flags wait all. That means I want both bit 0, okay, and bit 1 both to be set. Then only I'll be able to carry on. So the moment I call this OS flags wait, I will go to a block state, okay, until somebody sets it. Okay, and regardless of who runs first, doesn't matter. At some point of time, when thread 1 runs, it will set the flag 0 1. Correct. Then at some point of time, when thread 2 runs, it will set the flag 1 0. Okay, 2. So this is 1, this is 2. And that means at that point of time when both have been set, okay, that means in terms of the flags 1 1. Okay, the last 2 bits have both been set. So I can now unblock and go to a ready state. And I can then carry on from there when I finally get a chance to run. Okay, so in this example, you have multiple tasks that need to do something, and when they finish the activities, then only the third task can carry on. Okay, so this is also something that is useful, correct? That means if you have a particular task that must wait, okay, that means T1 must finish something, T2 must finish something, then only T3 must run. Okay, so using this kind of approach where a thread is waiting for multiple flags to be set and you want to wait for all, then you can do something like this. Okay, so in the lab manual, okay, that I have uploaded, okay, you are going to be trying out some of these, correct? The thread flags as well as event flags and message queues, and then you can see for yourself the different types of behavior. Okay, so there's a question, can we set the flag at the end of the function? Yeah, you can set wherever you like. It all depends on what is the behavior or the synchronization you want. Okay, that means you can move this right to the end of the while loop, that is just before I end. Alright, so it's up to you. You can use this whichever way you like, doesn't matter. Alright, it's just about giving you this concept that now I can synchronize this execution based on other tasks to complete certain activities, then this third task will carry on. How you want to use it is up to you depending on what is the objective you want to fulfill. Okay, so we do not set our own flags, okay, because there is no point in doing that, correct? Because if you are going to wait for your own self, you already know when you are already executing at that time, correct? So it doesn't make sense to set your own flag, alright? So you always set the flag for tasks that you want to synchronize with, okay, that could be waiting for you, okay, to achieve complete something, and then you signal them. All right, then if you want to wait for somebody else, then you use a thread flex wait call and let the other task signal you. All right, so this is one uh, sort of tool. Now let's look at the next one. Very similar to thread flex, but it's called event flex. Okay, it's called event flex. The only difference is they are not tied to any particular task. That means they are not created with the task. They are generic uh, sort of flag mechanism. So what we need to do is we need to first create a flag object. Okay, we need to create an event flag object and then we can use it. So the idea is exactly the same as thread flags. Okay, it's exactly the same. You have 31 event flags. Okay, the only difference is it is not tied to any task. Okay, so you first need to create it by calling event flags new. Then you can set and you can wait. Okay, so the behavior is the same. So if you look at this code, we are achieving the same LED behavior. All right, but the only difference is instead of writing to each other tasks flags, you are now writing to a generic flag. Okay, event flag. So what I need to do is in the main task, all right, I first create this flag called OS event flags new, and I capture the ID of this event flag. All right, so I also need to create this event flags ID variable. Okay, once that is done, then in this same scenario, I on the LED. Okay, then I set event flag. But now, since it's a generic flag, I need to specify which event flag I'm talking about. Okay, so this is to set for LED flag, event flag, and I set a value of 1. And this LED off is waiting for the LED flag uh, 1 to be set. All right, and then I carry on. So the behavior is the same. Okay, the behavior is the same. It's just a matter of whether I want to use the built-in thread flags or I want to use event flags. Okay, but the concept is exactly the same. Okay, so this is also something you can try out and you can see sort of how it behaves and how it works. Okay, now we go to the more interesting one, which is the message queue. Okay, so when you look at event flags and thread flags, all right, the key idea is synchronization. That means you want multiple tasks to sort of synchronize the execution flow. Okay, but there is no transfer of data involved. Okay, and that is where message queue comes in, because message queue achieves both at the same time. Okay, you can transfer data while achieving synchronization at the same time. So this is like a two-in-one solution. All right, which is very useful. Okay, and you might want to use it. Okay, or you might still want to choose event flags. Okay, but let's see how this works, and then you can decide later on. So in a message queue concept, you will create a message queue first, where you specify the number of messages and the size, all right, and any attributes that you want. Okay, wait, let me just answer. If multiple processes can write to the event flag, do we have to mutex it? Okay, so you do not need to use mutex for event flag, because once you set the event flag, whichever task that is waiting in the queue first will get it. All right, so if there are multiple event threads waiting for the same event flag, okay, then that one, whichever flag was waiting for it, will be able to get it first. All right, then the rest of them will wait in time for the next time to be set. Okay, so you can sort of see the behavior. Okay, that it will have the idea that somebody put the flag and then whoever is waiting first will get it. Something similar to semaphore, all right? That means if there are multiple tasks waiting, whichever task is first in the queue will wait first, and then the next person to post will go on to the next person in the queue and so on. Okay, so in message queue, so coming back here, message queue, you first create a message queue, all right, and then one task can put to it. Okay, when you put a message, you specify which message queue you're talking about, then the pointer to the message, all right, and these are two important things, all right. Then the other one is again the get the message, that means to retrieve the message, again the message ID and the message pointer. Okay, so let me explain through an example. Okay, then I think it's easier for us to relate to it. Okay, so how can we use message queues in the project? Okay, so I'm going to show you an example, okay, which you're also going to try in the lab. All right, and if you feel it's useful, you can use it. All right, so one thing that you can first do is you can declare a message data structure. All right, so in this case, I have intentionally put two 8-bit values to sort of create this structure. Okay, so my idea is I have two variables. Okay, one for command, one for data. Okay, of course you can just say that maybe one 8-bit value is enough, so I don't need two. All right, that is also fine. Okay, but in this case, I just intentionally use two separate variables to show that it can be expanded. All right, because the idea of message queue is I can send actually whatever data that I want from one task to another task and retrieve that data while I'm synchronizing at the same time. Okay, and then so once I declare what type of data structure that I want for my message, I will then create a message queue ID. So in this case, what I'm doing is I'm having three message queues for the three different tasks. One is for red, green, and blue. Okay, and I'm going to create three different message queues, okay, for the three different tasks. Okay, and each of them have one a message count as one. That means any point of time there's only one message that's going to go in, and then the size of my data packet and null. Okay, so now the next thing that you might want to think about is how are you going to populate this data packet that you have. So in this case, I have 2 byte information. One is command, one is data. All right. So I can specify maybe a value here for the LED and another data here to blink. Okay. In the lab, basically what I'm going to be doing is I'm going to specify the rate of blinking in my data packet. Okay. So depending on what data value there is, okay, I will blink at different rates. Okay. So, and the task. Okay, so in order for the three LED threads to start processing, somebody must send out the message, correct? Because somebody must send out the message and then you process the information. So in your case of the project, you can say that maybe your T-brain task, okay, is the one that will post the messages to the different tasks, correct? Motor task, LED task, and so on. Okay, so in this case, what I've done is I created a sort of a simulated control thread that will put messages into the different queues. Okay, so I will put a message specifically for the red message queue or the red thread, for the green thread, and for the blue thread. Okay, and each time that I put in, I specify the data. All right, so in this case, if I put 1 and 1, that means all of them get the same data. All right, that means everybody will sort of interpret the data in the same way. Now, for the three tasks or the three threads, how do I write the code? If you look at it, okay, firstly, I need to create a variable, which is the same data type as the one that I'm sending. And then the first thing I do is I call OS message queue get. That means each thread will be always blocked until somebody sends the appropriate message. All right, so in a sense, it is similar to how your motor should behave or LED should behave, because your motor should not move until it receives the command that it should move. Correct? LED should not blink until it receives a command it should blink. Okay, so until then, you go to a block state. Okay, the moment I receive a message, I will be able to unblock and I go to the next line. Okay, so in the next line, what do I do? So if I come to the next line, that means somebody has sent me some data, and that data is inside this my RX data. Okay, the data that has been sent to me. All right, and we know that this RX data has it's a data structure with two elements, the command and the data. Okay, so then I can now decode the value. Okay, and when I decode the value, I can decide what to do. So in this case, it is I'm just blinking the LED, okay, as long as the command is 1 and the data is 1. But in your case, you can have your switch case or if else statement here to look at the different possible commands, correct? If it's forward, what to do, if it's left or right, if it's stop, what to do, and so on. So you can decode based on the received data packet. Okay, so that is one way in which you can design your architecture, where you create a main control thread and you have individual tasks to handle different activities, and they will only trigger as and when new data is sent from the T-brain task. Okay, so this is one possible architecture. Okay, so in this example, what will we see? So if you see down here, the very first time I put a red message and then I block. So in this case, since I do a block, OS delay, I block myself means I will not be able to send the second message, correct? So this is message 1, this is message 2, this is message 3, correct? So after I send message 1, since I block I will not send out message 2 until I finish that 2-second delay. All right. Okay. So in this case, I am intentionally doing the block because I want to see the LED effect. Okay. So I first send out the message to the red LED. So when this message goes out, only this task will unblock and control the LED. Okay. Similarly, when this message 2 goes out, only the green LED will be executing. A green LED task will be executing. Okay, and finally, when the blue message task goes out, then the blue LED task will execute. All right, so that part is easy to see. Now, in this, I send out 3 messages together. So this is message 4, 5, and 6. So message 4, 5, and 6 all go out together, correct, one after another, correct? So what is going to happen? So when I put out these 3 messages, what will happen? So the first time the red message will get unblocked, correct? So the moment the red message or the red LED thread unblocks and it decodes the message, okay? At that same time, while it starts to execute, all right, since I did not block the control thread, okay, since I did not block the control thread, I will also be able to send out the green task message. Then I will also be able to send out the blue task message. Okay, so concurrently, okay, because of the round robin nature, all the 3 tasks will get unblocked and all 3 will start to run at the same time. Okay, all 3 will start to run at the same time, which is also similar to how you want your robot to behave, correct? That means when you have a command that you want to move, you activate your motor, you activate your buzzer, you activate your LED and so on. So multiple tasks will sort of wake up, get unblocked and start to execute concurrently. So that is what you observe here when I put multiple messages one after another. So all the tasks will wake up or get unblocked and will be able to start executing concurrently. Okay, so when you run this code, basically what you will observe is you will first see red, green, and blue, and then you will see white. That means all 3 running together. Okay, and then the whole thing repeats. Okay, so this is a very good sort of framework, okay, that I'm sharing with you. But again, it's up to you to decide. Okay, some of you may just see that, why don't I just make my life simple? I just use thread flags and event flags and I can still do it, correct? Yes, you can still do it. Okay, so it's about deciding which approach is more or you feel more comfortable with, okay, and you want to use that. All right, so there is no restriction that you must use message queue or thread flags or event flags. You can use whatever that you wish, okay, to design your architecture. All right, but like I said, the main advantage between this and normal flags is that the queues have the ability to send data while synchronizing. Whereas thread flags and event flags is the synchronization part. Data you still need maybe a global buffer or something, and then you need to make sure you protect the access to it using mutex and so on. Okay, so you can still do it that way or you can do it this way. It's fine, both ways is fine. Okay, so basically you can see that okay, so that basically covers the event flags, thread flags, and message queue concept. Okay, so you do not need to explicitly clear the message queue. The moment you read the message, it is automatically cleared. Okay, so it's automatically sort of cleared from the queue buffer the moment one task reads the message. Okay, so you don't need to explicitly clear it. Okay, so it's a built-in behavior. Okay. Okay, so sharing data safely, I think this we have seen before in the earlier slides, all right, where, for example, a simple instruction like b equals to 10, okay? So even though in C programming, you may look at it as a single line instruction, when you compile it into assembly, it can be 2 or 3 lines of code, okay, depending on, because of the way the processor architecture is. You need to load from memory or you need to update a register and then you can write to memory. All right. So definitely most instructions would not be considered atomic, okay, at the C level. So in that case, you definitely having a potential issue of having this race condition, as you have seen before. That means in some cases it might work, some cases it might not work, because uh, you might have a context switch in between while you're executing a particular instruction. Okay, so in order to protect that access, you need to use the mechanism that we have seen before, where you have mutex, all right, to lock access, and then you make sure you unlock after that. Okay, in the ARM, like what we said just now, you do not have the ability to directly access or change content in memory. You have to only do it through the registers. So, which means that in most cases, you have at least 2 or 3 assembly language instructions. Okay, so you have to make sure that you protect any shared variable access using the appropriate mechanism, such as mutex. All right, so of course, one other way of avoiding shared data is using message queues, like what we have seen. So in message queues, you don't have this problem because you are explicitly sending a message from one task to another task. So no other task is coming in between to try and take the data from you. Okay, so in that case, you do not need to protect that data. You are explicitly sending it over in a queue to from one task to another task. Okay, of course, if another option is beside mutex, you can also consider disabling interrupts, because interrupts will also be accessing your shared data. Okay, so and in the case of interrupts accessing a shared data, you need to make sure that you sort of disable interrupts while you're accessing the shared data, all right, to prevent corruption. Okay, then another important thing is how do you create a reentrant function? So what is a reentrant function? Okay, so imagine that you have task 1 and task 2, okay, and both of them call a function, okay, function A. So this block of code that is function A is called by task 1 and is called by task 2. Okay, it's a common function, maybe some mathematical algorithm that you have written, and both tasks need to use the same algorithm. All right, now what would happen if, let's say, T1 was accessing this function, and halfway through you get context switch and T2 takes over, and T2 is now starting to execute this same function A from the beginning. Okay, is that going to be an issue? So in order for us to make sure that a shared function does not cause issue between different tasks, okay, we need to make them re-entrant. And the way to make them re-entrant is to make sure that any variable that you create must be a new instance, okay, and it should not be thread specific. Okay, and basically the main thing is, as long as you avoid any static variable within the function. So you know that if I create any function in C, if I declare a variable as static, then what happens? That means that variable content will be retained after I exit from the function as well. Correct? Compared to a normal variable, okay? If I just create a normal variable, that is considered a automatic variable. That means I create it on the stack of that task that is currently executing. Whereas if I call it as a static variable or declare it as a static variable, it will be declared in the heap, all right, which will be where the value will be retained even after I exit the function. Okay, so you cannot have this kind of static variables within a function that is shared between different tasks. So that is the way you need to make sure that function is re-entrant. If the function is not shared, that means if function A is only used by task 1 and nobody else use function A, then it's fine. Alright, but as long as that function is supposed to be a shared function, then you should not use this kind of static variables inside that function. Okay. All right. So basically, that brings us to the end of this set of slides. Okay. So it's quite straightforward, the thread flags, event flags, and message queues. Okay, so with this, you basically have everything you need to know to finalize the architecture. All right, so we have talked about mutex, semaphore, event flag, thread flags, and message queues. And all of this is basically enough for you to finalize the whole architecture of how you want to design your project. Okay, and like I said, as long as the whatever requirements that are fulfilled or specified in the document is fulfilled, that is fine. Okay, so there are some guidelines on how number of tasks, and like the serial must use interrupt and things like that. So those kind of uh, sort of small constraints you have to follow, but the overall architecture is up to you to design. Okay, so there's no restriction on that. Okay, so that is something you can decide and you can build upon. Okay, so before I go to the demo, please remember that this Friday is a public holiday. All right, so the labs will be closed. Okay, so do not come to school, do not come to the lab. All right, but the lab sort of material is mostly just trying out the event flag, thread flag, and message queue. So as long as you have your board with you, I think there's no problem. Okay, you should be able to try it out. Okay, so let me end this slide here. And let me move over to the demo. Okay, so give me a minute. Okay, so in the lab, when you look at the lab manual, there is thread flags and event flags and message queues. Okay, so the thread flags and event flags, I will not show here. You can try it out on your own. I'll focus on the message queue part over here. So in this message queue part, basically, what you can see is I have created, besides the three tasks for the red, green, and blue, I've created one more, which is the control thread as well. Okay, and I've created the three message queues, okay, as shown in the lecture slides. Okay, now if you look at this, once I call OS kernel start, which task will run first? Red, green, blue, or control? Okay, what do y'all think? Is it going to be red, green, blue, or control? Okay, so since there are no changes in any of the priorities, correct, all are default, that means the task that is created first will run first, correct? That means the red LED thread. Okay, followed by green, blue, and then control. Okay, so that is the sequence, okay, based on the sequence that was created, the tasks were created. So let's look at the red, because all of them are the same. So let me just look at the red one. So if we look at the red one, the red LED thread, basically like what I showed you just now, the first thing I try to do is I try to get a message. Okay, and since nobody has sent me any message yet, I will go to a block state. Okay, so similarly, once I go to the block state, the green will run, it also wait for a message. Nobody send, go to a block state. The blue will run, nobody send, go to a block state, and finally the control will run. Okay, so when the control thread runs, what do? I populate my data packet. So if you, for my data packet, the command, I fix it as 01, but my data, I change it for different tasks. So the first time I put 01, then I put 02, then I put 03, and then I put 04. Okay, why? Because in the lab manual, basically what I ask you to do is to blink the LED at different rates depending on the data packet value. Okay, so in this case, I will put out, okay, this message onto the red thread. After I sleep for 2 seconds, then I will put this onto the green task, then put this onto the blue task, and then the last one, 4, is where I put all three together. Okay, so basically the very first time, okay, when I put to the red task, only the red task will get a message, so it will unblock and process it. So let's look at what happens. So when the red task unblocks it or receive the message, it will be able to unblock. So once it unblocks, it goes to the ready state and then it runs. It will be able to look at the command. So the command is fixed at 1. Then it looks at the data. So the data in this case is 1 means I have a delay of 1000, 1 second. If it is 2, is 500 millisecond or 250 millisecond or 125 millisecond. Okay, and then I do the on and off. Okay, so similarly, I do the same thing, okay, for the different tasks, except that I pass in different data packet values to indicate different delay timings. Okay, and in the last case is where I send out all 3 messages at the same time. So concurrently, all 3 will execute. Okay, so let's see how it behaves from the LED when I run the code. Okay, so this is the LED board. Okay, so let me run. So first is red LED, then green, then blue, and then followed by white. So if you look at the blinking red, first is LED red for 1 second on, 1 second off, then green, and then blue, and then white. Okay, so the rate of blinking increases, okay, for each LED until all 3 blink together. Okay, so the way this is working is of course through the message queue idea. All right, that means you are able to send out messages to different tasks. Okay, and each task will take that incoming data packet and process it and then carry out its activity. All right, so this example again sort of gives you that overview on how to do it. All right, and then in the earlier part of the lab manual, you also try the thread flags and event flags. Okay, so does anybody have any questions on this? Okay, will the priority of the functions matter? I mean, if you change the priority, things will change. Correct, because a high priority task will always uh, take the CPU first. Correct, the moment a high priority task is ready, it will run first until it gets blocked. Okay, so if any one of the tasks is higher priority, all right, then in that case, that task will execute until it goes to some block state, then the other task will get a chance to run. Okay, so if you change the priority, things can change. All right, so that is something that you can try. Okay, in the past, I think most students found that keeping priority equal across all the tasks was fine. Okay, so I do not. I mean, if you wish to try with different priorities, you can. Okay, but I think for most students, from what I know, they felt that keeping the priorities the same was fine. Okay, if you run control ID first, okay, to send out the messages also can. Okay, the reason why I do it this way is intentionally to replicate the concept of how the project will be. Because if you think away from the robot concept, the moment you power up your robot, you do not expect that already a button has been pressed through your Android and you straight away start moving. No, correct? The moment the robot boots up, it should be in an idle state, waiting for the command. Correct? So all the tasks will sort of start up, but they will all be in a block state, waiting for that first message to come in. All right, so that is why the control ID is intentionally put last, because that is sort of mimicking the sort of command you send from the Android phone. Okay, so all the tasks that you're going to be developing will run, but they all go to a block state, waiting for the next information to come in, and then I process it. Okay, so that is why I intentionally did it this way. Okay, so let's go for a break now. Okay, and about 10 minutes time, now it's 10:55, 11:05, we will come back here, and then we can go through the next set of slides on memory. All right, yeah, and then we can discuss their concepts. Okay, so I'll see you back here in 10 minutes time. Okay, so there's a question on the tomorrow. Okay, so the lab, Monday to Thursdays, the lab is fully booked for the EPP module. Okay, so if you want to use the lab, uh, I mean, if you need to do some soldering or things like that, then what you can do is probably you can email Uncle Jalil first, okay, and see whether he can allow you access either before the lab starts. That means you come in before 9 a.m. All right, or maybe before 2 p.m. Okay, then he can give you some time to do some soldering or things like that. Okay, but once the EPP lab starts, okay, because of the current restrictions, we can't let other students come in. Okay, so I will see you all back here in 10 minutes time. Okay. Okay, so this next set of slides is more generic, all right, to have some idea of memory and how memory is allocated and how OS helps to manage its memory internally. Okay, so it's a good sort of understanding to have, correct? Because in all embedded systems, one of the key constraints is always memory, correct? Because you have a finite amount of memory, all right, that you need to work with, okay? And this is quite important if you are dealing with systems where you need large amounts of space because of the data you're processing or the algorithms you're running or things like that. Okay, I've seen in the past students, they start off the project using one embedded board or something, and then towards the end, then they realize that they run out of memory, because they have to do so much of signal processing or some kind of transform algorithms, and it takes a lot of space, and then you don't have enough memory to store your data. Okay, and then you are stuck, correct? Because you spend so much of time working on this particular board and this architecture, and then now you don't know what to do. Okay, so it's always good to be aware of your memory usage of the system. Okay, and if you're working on a project, try to look for some platform or board that has more than enough memory, so that at least you know that when you start the project, you can finish it with that same development board again, and you don't need to switch halfway. All right, so in terms of this chapter here, we're going to be looking at the different components of the process memory, all right, and how memory is allocated, and some of the mechanisms that the OS helps us to or uses to help us handle memory. Okay, so let's break up the memory first into different sections. Okay, so the first thing is text. So when you write your code, okay, and you compile it, that code space, okay, the amount of space that your code takes up, that is basically goes into this space called the text segment. All right, and this is known in advance. All right, so the moment you compile the code, we know it in advance. All right, and that is basically stored in the text segment of your memory. Then uh, the next is your static data. So what is static data? Static data is basically refers to variables, okay, or data storage spaces that exist for the entire program. That means the moment I boot up the system till the end of it, it will always be there. and that is for global variables as well as static local variables. Okay, so when you declare global variables, let's say integer x, okay, so that is outside of a function. Okay, but if I have a function void function a, okay, and inside there I declare a static variable. Okay, so these are both what we call static data. Okay, only thing is this is global, this is local within the function, but in either case uh, they will both hold on and retain their values throughout the entire program. All right, and this is also known in advance. All right, so during compile time, the compiler will allocate these variables into one of two places, either data or bss. So data refers to variables that have been initialized in the code itself. So if I have anything like this where I declare this as a global variable, then it will go to the data segment. Okay, but if it's a static or local a global variable that is not initialized, okay, then it goes to the BSS segment and it will be by default set to 0. All right, so these are two separate segments in the memory, okay, that you can allocate static data to. The next one is dynamic memory. So in dynamic memory, it is when memory is allocated during program run. Okay, so for example, you have some incoming image data, okay, image signal, you do some signal processing and you have the incoming image data. So you may not know how much memory you need until that raw image information is available. Correct. Then only I know how much space I need. Then I can allocate, okay, using the malloc function. And once I'm done, I free up the memory. So this is something that the OS does not know in advance. Correct. So we need to set aside some memory for that. So that is basically what we call the heap. Okay, and this you need to have some space, okay, for the heap to grow as and when the memory requirements are there for the system. Then the other one is the stack, okay, for temporary variables, okay, that are created whenever you call a function. Okay, so whenever you go to a function, so you need the stack for two things. Okay, one is of course the variables that you need to create in that function itself. At the same time, when you finish the function, you need to return back. Correct. So all this return address is also stored, okay, within the function, within the stack. Okay. So generally for a stack, we relate it to what we call the push and pop functions. Okay. So at the assembly language level, usually there will be some equivalent push and pop instructions. All right. But again, that is done when you compile. Correct. When you write in the code in C, you do not worry about it too much. The compiler handles that for us. Okay. So in this generic view, okay, we can say that when you write a piece of code, okay, as it is, you will occupy uh, or different parts of the code will go to different sections in memory. Okay, so of course, all of this have some addresses allocated to them. Okay, so for example, over here, I might say this is starting from address maybe A000, and this is starting from 0x. A0 or A100 or something like that. Okay, and this could be 0xb000. Okay, so I'm just giving you some random addresses. Okay, but generally all these are specified in another file. Okay, so that is known as a linker file. Okay, so we're not going to the linker file, but when you click on build, okay, or compile in your environment, you compile the code, correct? But while you're compiling the code, okay, the linker file is also integrated where your compiler will look at the linker file to know where we have specified the different memory regions so that we know where to map these different regions to. Okay, so that is how your compiler is able to know whether you have exceeded the memory, correct? Because in the linker file, it will have specific memory ranges for text and data and so on. So sometimes, if let's say your microcontroller board only has 8 kilobytes of memory for text. Okay, but your code is so big that it compiles beyond 8 kilobytes. So when you compile already, it knows you've exceeded. Okay, so it will give you an error message that you've exceeded the size limit. Okay, how does it know? Because the linker file will have all this information for us. All right, all these memory ranges for the different segments of memory. Okay, so in terms of stack, okay, let's look at stack. So if I look at this function here, main, okay, and inside main itself, I have three variables that I've declared, and then I call a function I call a function f, where I pass in two parameters a and b. So a map to x, b map to y, and inside f, I again create another local variable, okay, and then I do some computation and I return. So how will this look like generally, okay, in terms of how stack will be used? Okay, so when I first run my code, okay, since the main program itself has created three local variables, okay, this is what we call automatic variable. That means they are created as and when the function is invoked. Okay, so the main function is currently running, so I occupy or set aside some memory for these three variables that I have. Okay, and then subsequently I call the function f. So I call the function f, I create three variables. Okay, so of course besides this, I also store the return address, correct? Because at some point of time when I return back, I need to come back to this line over here. So this return address is also stored on the stack. Okay, but that is not shown here. We're just looking at the variables. Okay, and then after that, when I finish, then when I return from function f, basically you pop everything out from the stack. So the stack pointer is now back to where it was before the function, correct? And then finally, when I finish the main, I exit. Okay, then I clear off everything from the stack. Now, if in our ARM controller, if I call a function c equals to f a b, okay, let's say this function is now being executed on my microcontroller board, correct? The one that you're using right now. Will A and B go onto the stack? Yes, no? Okay, so that's one answer. How about the rest? What do you all think? If this is now running on your board, okay, the one that you're using, and I have a similar function A and B, do you think it will go onto the stack A and B? Okay, so let me just share with you. Okay, so this is not, I mean, it's something you'll probably learn in another module, which is where you look more into the architecture of ARM. All right, so for ARM, okay, so this is, I would say platform specific or processor specific. So in ARM, they have this protocol called the ARM procedure call, APC. Okay, where when using an ARM processor and you're going to call a procedure or a function, okay, they have a rule. So the compiler, what it will do is when you have parameters to pass into a function, the first four parameters, okay, the first four parameters will actually occupy R0 to R3. So your ARM has a lot of registers. Okay, so we do not go into those register level details because that would be looking into assembly language coding and all. All right, so if I were to go into that, then this whole module will become like two modules. Okay, so but in assembly language, okay, ARM, if you look at the register level detail, you have a lot of registers. So R0 to R3 is basically what the compiler will automatically set aside for parameter passing. Okay, so if I have only two variables like this, A and B, then I will not use the stack. Okay, in the ARM processor architecture, I will use two of these registers, R0 to R3. I will set aside two of them to do this. Okay, and the idea is simple. You want to, because register access is always the fastest. Okay, because register is internal to the processor. Okay, anything that's outside the processor will always have some added time delay. Okay, so as much as possible, if I can settle everything within the processor space, I can speed up my execution a lot. All right, so that is why it uses internal registers as much as possible. If you have more than four variables, or if R0 to R3, you cannot free them up for some reason, then the stack will be used. Okay, so this is just for your information only. All right, this is probably something that you should cover in another module, I think. Okay, where you look into the ARM assembly language programming. Okay, so now let's look at an example here, okay, of a code, and let's see how it will actually sort of uh, be allocated to different parts of the memory. Okay, so you have this function here, and then you have two variables, string length and I size, global variables. Okay, so let's see what happens. So firstly is the whole code. Okay, this entire code block over here will go into the text segment, okay, of the memory space. Next is your global variables. So in this case, uh, you have a global variable here that is declared or initialized. Here you have another static local variable that is also initialized. So initialized variables will go into the data segment. Okay, then you have a global variable that is uninitialized. So it will be assigned a value of 0 and it will go into the BSS segment. And then you have a malloc over here. So this is runtime memory allocation. So it will, when you execute this code, you will make use of the heap segment, and the local variable here or the automatic variable here will occupy the stack segment. Okay, so these are all the different portions of the memory that you will occupy in this piece of code here. So when do you allocate memory? Okay, global variables and static variables you allocate during startup, and you deallocate when you finish. Okay, for local variables, you allocate when you make a function call, and when you finish or you return from the function call, you deallocate. And for dynamic memory, okay, you malloc and then you free. Okay, so let's look at an example here. So in this case, you have a malloc function, all right, and you're allocating different sort of chunks of memory. So first I allocate 3 blocks of memory, so malloc, and I assign it to P1, and then I allocate 1 block of memory, and then another 4 blocks of memory, and then I do a free. So when I free, what happens is I free up this space over here. Okay, and then I allocate another memory for 6 blocks, and then I free P3. So P3 that was there also gets freed up. All right. So of course, when things get freed up, you create what you call holes in the memory. All right. So later we will look at how to resolve this. Okay. How do I compact my memory to better manage it? Okay, as more and more requirements for memory come in. Okay, so in this case, since the slot here is now free, when I have allocation for 2 blocks of memory, I can now go back to where P2 was free and allocate from there. And then in the end, I free up everything. Okay, so this is just giving you an idea of how the allocation works, okay, in the system. And then later we will look at what are the other things that the OS can help us do in the back end to better manage the use of memory. Okay, so now another critical thing is how to avoid problems with memory. All right, so this is quite a important thing, because these are the kind of I would say things that we may overlook in our code, and it does not flag off as an error, and your program system just works fine. Okay, it works fine for 1 day, it works fine for 2 days, and then 1 week later it crashes. And then you say, never mind, I just reboot. Then 1 week later it crashes. Right? Then you realize every week it crashes, but you do not know why it's crashing. Okay, so these are the kind of bugs that are very, very difficult to find. Okay, because you really need to look at what you are doing with memory. Okay, so in this case, what is happening is you can see that in this function f, every time I call f, I allocate some memory. Okay, and I return without freeing the memory. So as far as the system is concerned, you allocate, but you did not free, means that allocated memory is considered already used up. Okay, so maybe you call this function f every periodically, maybe 1 hour once, or every few hours once, depending on what your system is doing. All right, so you may not see any effect, all right, initially after a few days and so on, but at some point of time there will be an event where you try to do the malloc and it fails. All right, and then if you did not handle that failure properly after that, you may end up overwriting some other memory, or point to some other memory that is belonging to some other function, and then you do some corruption and the whole system just crashes. Okay, so these are the kind of things that a compiler may not be able to pick up. Okay, but generally compilers nowadays are very smart. Okay, they tend to pick up these kind of things as warnings. Okay, but what happens most of the time, we don't look at warning. All right, as long as can compile, can download, can run, we are happy. All right, so this is a good thing to always look at the warnings to just see whether there's something that is an issue. All right, so this kind of code, okay, if the compiler is smart enough, might be able to give you a warning that memory allocation was done, but no deallocation was done, or something like that. All right, then you can at least look at the code to see whether uh, why you did it this way. Is it intentional? Maybe you're going to free, maybe it's a global pointer and then you free it somewhere else or something. Okay, so it's always good to check that every time you allocate, there is some point where you deallocate. Okay, if not, you will use up the memory and then the system will crash. Okay, so this is also another dangerous thing to do, where I create a local variable. Okay, I create local variable. So this p is valid, correct, within this space of this function. But again, all these are created on the stack. So the moment I come out of this function, I return from this function, this p is no longer reserved for this variable, okay, or whatever that I was doing here. But I can still do this, correct? I can still do this. And what will I get? That means this result here will point to the address that was originally allocated for this array. Okay, so but that same memory location can now be overwritten with some other new data, okay, which we do not know what is going to reference to. Okay, so your compiler again may not pick up this kind of things, all right, and you might think that since there is no compiler error, it is fine. Okay, but it is not, because you're pointing to data that is no longer there. Okay, it might be there, correct, but it can always be overwritten anytime because it is part of the stack. So some other function call, some other event can always override the stack. Okay, so these are the kind of things that are also dangerous to do. Okay, you are pointing to some unallocated memory. Okay, so memory allocation is again requested and granted, okay, while you are running the code through the malloc and free functions. Okay, now let's look at some example of malloc. All right, so in this case, I create a call malloc to set aside 4K bytes of memory, and I use the pointer here to point to the start of this memory location. So this 8192 is basically the address of where this 4K byte is starting from. Okay, so then from there I can access this entire memory region using this pointer over here. So when I use malloc and free, Okay, what are the issues that can cause? Okay, so it can cause what we call fragmentation. Okay, and there are two types of fragmentation. One is called external, the other is called internal. Okay, so in external, let's see what happens. So in this example here, I have 4 malloc calls, all right, where I call malloc 100, okay, 100 bytes of memory set aside. So first, second, third, and fourth. All right, and now after I allocate these 4 chunks of memory, I do a free of the second and I do a free of the fourth. Okay, and now when I try to do this, what happens? Okay, it does not allow me to allocate. Why? Because I want 200 sort of bytes of memory as a single block. Okay, but I have more than enough because I have 100 here, okay, and 150 here, but I do not have 200 as one complete block. So because of that, this malloc will fail. All right, so that is the issue with this external fragmentation. All right, now how about internal fragmentation? So internal fragmentation, okay, let's say now the malloc is done based on a particular allocation unit size. So in this case, I say my unit size is 100. That means every time I ask, it will be multiple of 100 bytes. So in the first case, I ask for 90, okay, but I get 100 and I have 10 of it, which is free. Similarly, I ask for 120, I get 280 is free. And in the third one, I ask for 10, where I will get 100 and only 10 is used, 90 is free. So you can see that I have a lot of free space, but then the malloc of 50 will still fail. Okay, because I need, okay, uh, to have 100 byte chunks to allocate memory. All right, so you are still not able to fully make use of the amount of memory you have. So in terms of internal and external, all right, you need to think of which one is different OS may use different kind of allocation. Okay, so if I use fixed size allocation, it may lead to the internal fragmentation, but less overhead, okay, to keep track of free memory. Okay, so we'll look at that in a while. So in a normal example here in the external fragmentation, I always need to keep track of my next available space. All right. So from here, I need to know where is the next available space that I have for allocation. Okay, and where is the previous free space and previous occupied space and so on, so that when I want to allocate, I know where is this memory chunk that is free. Okay, so we are going to be looking at some rules on how this can work. Okay, so this free list is basically for us to keep track of the available memory. So in terms of the available memory, you can say that one is free and one is allocated. Okay, which is a hole and a chunk. So you can see here that this white space here is all the holes. All right, and this black space is the chunk. That means it is already used up. The hole is free. And what I need to do is I need to occupy some space of these holes to actually keep some pointers to know that where is the next available space that I can allocate memory to. Okay, so in this case, the next pointer must point to, from 100 here must point to 400. Then from 400, I must point to 830 and so on. Okay, previously, I similarly, I must also have the previous pointer to point back to know where is the previous hole that is currently available for me to use. Okay, so I need to build these pointers, or the OS needs to keep track of this information by having some pointers in these holes of the memory. Okay, so of course, how do you have this free list? You want to try and keep the holes as large as possible. Okay, so that even if I have a small request, I can easily fulfill it. Okay, and when I have fewer holes, which are large holes, then it's also faster for me to search in the memory. Okay, so let me go through this. So when I deallocate memory, what happens? Okay, when I deallocate memory, okay, I will put memory into the free list, and I need to update my next and previous pointers. Okay, so now let's look at this. So in this case, I have this chunk and this chunk that is occupied, and I free what is in the middle. So when I free what is in the middle, okay, I cannot do any merge in this case because these two are currently occupied and this is a whole. So I can leave it as it is. Now, if I have this where the earlier chunk is now freed up, okay, that means if currently this is a whole, the first chunk is a whole, and then I do a free in the middle, then I can do a merge. So this whole chunk here becomes one big whole. Similarly, if I have a hole after that and I free up the block before, okay, then I can do a merge with the hole after. Okay, so whenever I do a free, okay, it is possible for me to do a merge with the hole that is either before or after, okay, the current block that I'm free. Okay, so I can also merge with two holes, okay, and make it a one big hole over here. Now, let's look at this example of deallocating memory. Now, in this case, okay, I have this previous pointers and next pointers built in. At the same time, I have some holes and I have some chunks. Now, what if I do a free? So this current chunk of memory here that is occupied, if I do a free. So once I do a free, that means I can see that since here there is a hole, and now here I've done a free, I can do a merge. I can do a merge between this free space that is currently available and the hole that was already there. So in order for me to do this merge, all I need to do is to readjust my previous pointer, okay, and my next pointer. So once I do that, this whole chunk will now be freed up. All right, so that is basically one of the ways in which you can allocate or deallocate memory. Now let's look at how or some of the algorithms that the OS may use. Okay, so sorry, I missed this question. I think what if there is a tiny chunk between two holes, not possible to shift and merge? Okay, so to shift and merge, okay, requires a lot of effort. Okay, conceptually, when you think about it, you can draw it out and say it's so easy, correct? I mean, if I were to draw it out, it might look like a very easy task. Right? This is occupied, this is occupied, and this is empty. All right, but in terms of the actual work that needs to be done is quite a lot, correct? Because I need to move this entire chunk over. All right, and what if when I move, there is also some more memory here? Do I move everything? Okay, so some of the sort of approaches that the OS might take would be something that is a balance between trying to free up the memory, but at the same time not overdoing it. Okay, so it will try to do as and when certain rules have been fulfilled. Okay, so in this case, again, doing it this way may be more challenging. Whereas if I just wait for this chunk to be freed, then I can merge these two together. Right? Because if I start to shift, then what happens to the memory after that? Okay, so if the rule says every time I shift, then there's going to be a lot of work being done at the background to keep on shifting and clearing up all the holes. Okay, so as much as you want to optimize it, you also do not want to overdo it. All right, so that is the idea. Okay, so in terms of allocation algorithms, okay, we are going to look at a few algorithms here. So the first one here is the best fit. So in the best fit, we look at picking the smallest hole that will satisfy the request. So in this case, I have three holes, okay, and I look at the smallest hole. Okay, so though it is good, okay, that I look for the smallest hole that is just nice for this, it leads to me having to search the entire list every time, and also tends to have a lot of small holes. Okay, so after I allocate, you can see that I will still have another small chunk of 50 that is still available as a whole. Okay, so it leads to a lot of external fragmentation. The other one is worst fit. Then I pick the largest hole. Okay, so again, it leads to me having to search the entire list and also causes fragmentation. The next two is basically the first fit and next fit. So the first fit means I always look at the beginning, and from the beginning, I look at the first hole that is large enough to satisfy the request. So in this case, if I want 150 bytes, if the first hole is already 1000 bytes, I straight away take it. Okay, but I always start from the beginning. Okay, whereas in the next fit, I start off from where I stop. So if I want, let's say I wanted 800, okay, then I allocate here. Okay, let's say I wanted 800. So I stop here. So I know I have 200 left. Okay, but let's say my next allocation is 300. Okay, then I look at where I stop. If it's 300, then I go to the next hole. But if let's say it is 200, then I can straight away take this. Okay, so I start off from exactly where I left off, and then I carry on from there. So that is next fit. So it's just an extension of the first fit. Only thing, you start from where you left off. Okay, so in terms of compaction, all right, the internal fragmentation, okay, you can use paging or segmentation, okay, but we will not be covering this. To deal with external fragmentation, we can do compaction, okay, so that is what we're going to be looking at. So this is what I was talking about just now. All right, so in this case, you have a hole and you want to shift and clear up all the holes to compact the data. Okay, but like I said, conceptually it is easy to see, but it's actually a lot of work, okay, at the back end, okay, by the system. All right, so how do you do this? Okay, you just basically move all the memory to one end of the system. Okay, so you keep on combining all the holes to form one large hole at the other end. Okay, so in your system, you always have one side which is one complete chunk which is occupied, and one hole which is one large hole which is free. Okay, so of course, uh, though it would be good to have something like this, it's always a lot of overhead. All right, because you need to keep on adjusting all the pointer values, you need to copy all the data over and so on. Okay, so that is a challenge. Okay, so one way to go about this is to have this concept of what we call the multiple free list. Okay, so in multiple free list, basically what we do is we keep lists of different hole sizes, and then whenever I have a request, I look at which one matches the size that I want. Okay, so in this case, you can see that I have uh, blocks for different sizes. So 256, 128, 64, and so on. And each of this gives me memory block chunks of a particular size. And that means when I want to look for a memory, I try to go to that particular list and take a memory slot from there. Okay, so that is another way of managing it. All right, so in this case, for example, if I start off with the largest size, then I speed it up. Okay, so I have 8 megabyte here and I have 8 megabyte here, and I speed it up into 4 and 4, and I can speed it up somewhere as well. All right, so at every time I divide, I split up into by 2, and I keep dividing until I reach the smallest one that I want. Okay, so in this example, okay, if let's say I want 100K, okay, and I'm using this multiple free list approach, okay, what will I do? So in the OS, what it will do is you will first create the list like this. So you, okay, where 1 megabyte will be split up into 512K, 256K, 128K, and then from 1 to 8K, you will allocate one of the holes. All right, and of course, part of it is still free, but it is fine. Okay, so that is basically how the free list approach will work. Okay, when the OS manages the memory request. Okay, now an extension of what to do next is the buddy system. So in the buddy system, basically what we do is we come back to the same free list, and then we look at what are the buddies. That means for every memory division that we do, it has a buddy which it can pair up with to close up and create a whole. Okay, so in this case, for example, okay, this 2k and this 2k can merge together and create a 4k whole. Okay, but whenever you do a merge, it has to be aligned to the boundary at the one level up. So in this case, this 2k and 2k are not aligned, so they are not considered buddies. All right, so this actually is a good system. Why? Because when allocation, you speed up until you get the size that you want. When memory gets freed up, you are also able to compact them together based on just that particular level. Okay, and then you compact that two memory chunks together. All right, so when you are allocating, you allocate by breaking it up until you reach the correct size, and then when you merge up based on the one level higher. So let's look at an example here. So in this case, you have 1 megabyte, and I ask you for 100k. Okay, so in this case, what happens is I will have 512k, 512k, correct? So I'll speed up 256, finally 128. So out of this, I have 128k here, but only 100k is used. Correct? I allocate 100k is used. And then I have another allocation for 64k. So what do? I split up the 128k into another 64 and 64. Okay, so you see that the OS is now able to choose the correct entry based on the list. So you have a list of different memory blocks sizes, and you choose the correct one that closely matches the request that is coming to you. Okay, now if I ask 240k, I will allocate from this block over here. Okay, so there's always some fragmentation, okay, because some memory is not used, but that is fine. Okay, because we are still trying to allocate based on the size that closely matches the request. So that memory loss due to fragmentation is still as small as possible. Okay, now if I ask for 256k, it will not break up the other chunk. Okay, allocate to me. And now when I free up 240k, what happens? So this chunk is free. So this whole 256k is free. Okay, but again, the moment I free, I do not merge. Correct? Because I only merge with my buddy. So 256k will only merge with another 256k, which is along the boundary lines of the one level higher. Okay, so if I free up another 256k, again it is there. But now when this 256k is free, this and two are buddies, correct? Because they align to the 512k from one level up. Okay, so in that case, they can merge together. All right, so that is basically how the buddy system works. All right, so it is a very efficient system because the memory loss due to fragmentation is minimized by choosing the most appropriate size. And at the same time, when you free, you don't need to have that large overhead of shifting huge chunks of memory everywhere and rearranging all the pointers. You just compact based on the buddy that you have. All right, so it helps you to manage your memory a lot better. Okay, this free list and buddy system approach. Okay, so basically it's a very short chapter just to give you an overview of memory and what is happening in the background. All right, so even though we did not go into too much of memory analysis and in the labs and so on, I think it's always important to be aware of the memory constraint of your system when you are dealing with whatever you want to develop. All right. So in this chapter, we sort of have a nice overview of what is happening in the background. Okay, so that brings me to the end of this chapter here. Okay, so basically next week, I just have one more set of slides, which is also quite short. All right, and then we will have some discussion on the exam. All right, the format, the structure, the type of question, and so on. Okay, then, and that will sort of end the whole module. Okay, the assessment will be in week 13, okay, the last week. So you will stick to your same lab slot, lab schedule. All right, and then we will have the assessment. Okay, more details on the timings, what will happen when you come for the assessment, I will update you all. All right, but for now, it will be in the last week of the semester where we will have the assessment. Okay, so the rest of the weeks, okay, you can focus on working on a project, okay, and getting it up and running. All right. Um, so I think from what I've observed so far, I think everybody is progressing well. If you have major issues that you are stuck and you really do not know what to do, you can ask your TA or you can also approach me, okay, and you can have a discussion on it. Okay, so that's all I have for today. Thank you very much. Any questions you can ask me. Okay, if not, I will see you all next week. Okay, so this Friday is a holiday. Okay, so please don't come to the lab. Okay, I'll see you all next week.